Hi guys, in this particular session we are going to look at the overview of the computer architecture. The computer is fairly complex device. A complex device always demands a good architecture. And this architecture is driven by the needs of the people and also the limitations, challenges, constraints that we face. And also it must facilitate the functionalities. In case of a computer, that is input, process, storage and the output. And also the modern computer is general purpose device. So our architecture must facilitate this general purpose nature as well. Computer is predominantly data processing device. So data is conceptual thing, and of course the process data is also concept. So therefore the computer is quite different from most of the other devices that we use in day-to-day life. For example, if you take a washing machine, we process physical things. If you take a blender, we process physical things. Or if you take something like a fan or a vehicle, we convert one form of energy to another form of energy. For example, in vehicle, we convert, say, petroleum vehicle. So we convert that chemical energy into kinetic energy. But computer is different. In computer, we process conceptual data into conceptual information. So therefore, the computer architecture must facilitate our need. And also, the modern computers process different type of data as well. It all started as a device for processing numbers or numeric data. But now it has evolved to be a device which can process text, images, audio, video, and new data types as well. Because of the Internet of Things, the various use of sensors, the new data types are also coming into the picture. So this is the architecture the computer engineers have come up to build the computer system. So it's a layered architecture. So remember, data is a conceptual thing. So our architecture has, in the upper layers, we have this conceptual, the software. In the very end, you have the physical hardware. And in between, we have the firmware. So therefore, the conceptual data is initially processed by software, and later in reality it is ultimately processed by hardware. So what is known as logic circuits or the logic gates. And again we are getting back the information, which is again conceptual thing. So we can think of it as the processing is happening at different layers. The application software layer, the system software layer, firmware and hardware layer. And it is the combination effort of these layers that process data into information. So let's first look at how the data is represented in computers. For humans, we work with different type of data, and those different type of data make different sense to us. For example, numbers are there, text is there, the images are there, audio and video. So they are different things for us. We remember those things or comprehend those things differently. We process those things differently. And also, when it comes to numeric things, they are quantitative. Whereas when it comes to images, audio, video, they are more qualitative things. But when it comes to computer, everything is quantitative thing. And therefore we represent everything as numbers or quantities. So that is the first thing we have to understand. Even the qualitative things are quantitative things in the computer, because computer is a computing device. And not only that, the modern computers represent those quantities in binary. That is not a big thing, because any quantity can be represented in any base. We store data in binary. We process data using binary logic. We call it Boolean logic. And especially inside the computer, we transmit data also in the binary format. So we call it binary digital signals. So why we are always interested in binary? As humans, we use denary system or the base 10 system. So while we are using the base 10 system, the computer engineers have designed the computer in such a way that we represent data in the binary way. And also we are sending binary digital signals. So there must be a reason for that. So there are two main reasons. The first reason is, as I already mentioned, we process data using Boolean logic. So Boolean logic is two-state logic. Always the result of Boolean operation is either true or false. So Boolean logic is a binary concept. So therefore, if we represent data also in binary format, those two are highly compatible. The second reason is maintaining two-state in storage and transmission is much more simpler than maintaining 10 states. If we go for denary, we have to maintain 10 different states. And nothing is perfect. The charging levels, the voltages, they tend to deteriorate. So then earlier, if the level is 8, now if it has deteriorated, we never know whether it's 7 or 6 or still 8. So there is a confusion when we have 10 different states. But when we have just two states, it is just on or off, present or not present, which is much more simple than working with 10 state or the denary. So that is those are the two main reasons why the computer engineers have settled into the binary system. So then what is meant by processing? We all know that all the data is represented as binary digits or binary quantities. So processing means either we are transferring that binary digits into different set of binary digits, or we combine or apply some calculations to get a new set of binary numbers. So how do we transfer the original binary data into the process data or the information? So remember, in the computer processor, we have a component or important part called arithmetic and logic unit, ALU. So obviously the name is because it does the arithmetic operation and logic operations. Since we are keeping the data in binary, so our arithmetic is also going to be binary arithmetic, the arithmetic related to base 2. And later we will discuss that the binary arithmetic can be done using Boolean logic. So therefore, though we call it arithmetic and logic operations, ultimately what we are doing is 100% Boolean logic operations. So therefore, if someone asks how do we process data into information? By applying Boolean logic operations. So let's dig into the technology little bit. So you may have heard two words, the electrical devices and electronic devices. So what is the difference between electrical and electronic? So electrical means we use electricity as the power source. But when it comes to electronic, while we power the device using electricity, we are interested in generating, processing and transmitting signals as well. So if you take something like a radio, television, computer, a phone, so they are electronic devices. So when it comes to electronic, there are two major branches: analog electronics and digital electronics. So digital electronics is the new branch, and the computer is a digital electronic device. So what is the difference? In analog electronics, we are interested in analog signals or continuous signals, whereas in digital electronic, we are interested in discrete signals. So in discrete signal means all of a sudden their energy levels change. It's not a gradual change. To be very specific, when it comes to compute architecture, we are interested in binary digital electronic, right? Because in digital electronic, there can be multi-states. But what we are really interested in is two-state digital electronic or binary digital electronics, because computers store data in binary, process data in binary, and transmit data in binary as well. So that is why we say that computer is a binary digital electronic device. And also let's look at the component architecture of the computer. So I told you that computer is a complicated device, and also computer is a general purpose device. So when we are designing a general purpose device, the engineers adopt the concept called component based architecture. So the idea is you design different components with well-defined tasks and well-defined interfaces, and we assemble them together. We integrate them together. So the result is easily upgradable, easily maintainable, easily replaceable architecture for the device. So that is why when we have some issues with our memory, we can simply replace that memory chip. When we are not happy with our hard disk performance, we can just take it out and replace with a solid state drive or SSD drive. So all those things are possible because we use component based architecture. The computer is not a one big monster. It's a well thought out combination of well thought out components, with each component having its own well defined tasks. So I told you that the modern computer is a general purpose device. So in order to make it general purpose device, the computer engineers and the scientists have come up with a particular architecture. So we call it the stored program architecture. So the original concepts came from Alan Turing. So he wanted to build a general purpose machine rather than building a computers for specific purposes. So then the von Neumann came up with a practical solution. So that is, load programs to the memory and let the processor execute different programs or different programs at the same time, but they have to communicate with the memory, because accessing memory is much faster than accessing the secondary storage. And the world's first general purpose computer based on the von Neumann architecture was ENIAC. And from that time onwards, now the computers are pretty much general purpose devices. So let's look at the overview of the hardware components. As I already mentioned, so we need input devices, the output devices, the storage devices, and the processor. So this is the von Neumann architecture of the modern computer, the general purpose computer. So you can clearly see the input devices, the output devices, the memory, secondary storage, the ROM, and the processor. So let's look at the components one by one. So the input devices are to input data and commands. For example, when you are logging to a website, so you type your username and password, so that is your data. So then you click on the login button, so that is you are giving a command. Maybe you are doing a word processing. So you type some data and then maybe you are saying save it or format it. So those are the commands. So then we have the output devices. The output devices are there to output the information. So the main output device is the screen if it is a general purpose computer. So then we have the printers and so many other output devices. So then we have the secondary storage. So secondary storage is used to permanently store data and programs. So the secondary storage includes either your hard disk or SSD, which is online. That means which is connected to your computer motherboard. And also secondary storage is non-volatile. So that means even after power is off, the data and programs will be there. And it's very important we keep both data and programs. So much of your secondary storage will be keeping the operating system and other installed software. So then we have the random access memory or the main memory. Remember the von Neumann architecture, the main memory has a key role to play because all the other devices transfer data through memory. So memory is your hub. So what is the purpose of memory? So the memory is used to keep currently running program segments and related data. For example, if you are currently doing a word processing, say Microsoft Word, so your word software, not entire software, part of the running programming segments are in the memory. And also your document is in the memory. So that is why you have to save it. And all the devices will be transferring data through the memory. So then we have the ROM. So ROM is the device that keep the firmware, the BIOS and CMOS. So we will be looking at the firmware in a later session. And finally we have the processor or the central processing unit. It does two main things, the processing and the overall control. The control unit is contributing to the overall control of the system as well as controlling the processing instructions. So that is the big picture when it comes to the von Neumann architecture. Right. So when it comes to input and output devices, those are the simple things, right? So the idea is to facilitate the input and facilitate the output. So the designing concerns are make those as user friendly as possible, like ergonomics and other things, and also try to make them faster and automate as much as possible. So then we have the storage devices. So when we say storage, both secondary storage and primary storage we take, including the registries. So there are different mechanisms the computer engineers have used to store data and programs in the computer. So the physical ways like punch cards, then the magnetism, the use of electrical charges, and even the use of the concepts of optics. So the early days of computing in 1930s, 40s, the people start using punch cards to represent data and program. Then people came up with the use of magnetism to store data. So the magnetism has been the key approach of storing especially the offline data, because magnetism is also binary concept. So you have the north polarization and south polarization. So therefore we can use it to represent the binary values, the 1 or 0. The hard disk, the floppy disk that we used to have, so they all used magnetism. So now we have the solid state storage as well. which is pretty much an extension of the ROM technology. And these SSDs, so the solid state storage devices, use the logic gates to store data. And also we are using the concepts of optics to store data and retrieve data. So we do something called burning the data, that is creating some pits and lands in the surface of the CD or the DVD, and later we use a optical beam to identify those pits and lands, which represent basically the zeros and ones. So the storage devices can be identified as a hierarchical structure. So when you go up the hierarchy, it is more closer to the processor, and also the speed goes up, but at the same time the cost is going up. And when you go down the hierarchy, the capacity goes up, because we need more and more capacity go in the down in the hierarchy. So let's start with the registries. So the registries are inside the processor, and registries can keep the currently running instruction and related data. So there are some special registries like instruction registries, status registries, and some general purpose registries to keep the data. So they are storage devices, and we need only few number of registries, and they are high speed because they are inside the processor. So then we have the main memory or the random access memory. So that is where we load our program segments and the data. So all the other devices access data from the memory. So then we have the secondary storage, which keep the programs and the data permanently. So SSDs and hard disks. Finally, we have the tertiary storage, that is the backup storage, like your pen drives, CDs, DVDs, etc. So while we have this memory hierarchy, so we have another component that keeps the firmware of the computer. So that is your read-only memory or the ROM. So those components make your storage devices. So now let's look at the processor or the processing device. In modern computers, the processing device is called the microprocessor or the CPU. So the microprocessor has two main components, the arithmetic and logic unit and the control unit. So the arithmetic and logic unit does the arithmetic and logic operations, whereas the control unit does the overall control. So we already discussed that when we say process, your data is, your binary values in the data is converted into another set of binary values by applying ultimately Boolean logic operations, because even the arithmetic is ultimately set of Boolean logic operations. Now let's see how do we do this processing. We can look at the processing as a different levels of things. So at the very high level, we have the processor. So your processor consists of logic circuit components like adders, encoders, etc. So these components consist of logic operators or the logic gates. And these logic gates are electronic gates. And these electronic gates can be built using transistors. So let's look at different levels. So all the data is processed by using something called electronic gates. So what is electronic gate? Electronic gate is a gate that either facilitates flow of electricity or prevent flow of electricity. So we say that the gate is open or gate is off. In other words, gate is giving 1 or gate is giving 0. So how do we make electronic gates? So in early days, we used to make electronic gates using vacuum tubes. So vacuum tubes is a vacuum container with anode and cathode. So when we apply a good amount of voltage, the electrons start passing through the vacuum from cathode to the anode. So when the electrons are passing, so we say that the gate is open. When the voltage is removed, again the gate is closed. So we use vacuum tubes in early 1960s and 70s, but it had a lot of drawbacks. It was big in size, a lot of power consumption, heat generation, and they were not that fast. So then came the transistor-based logic gates. So the concept of transistor was made possible by discovery of semiconductor materials. So semiconductor materials are materials which are neither conductors nor insulators. So the conductors allow free flow of electrons, whereas the insulators do not allow flow of the electricity. But when it comes to semiconductors, under certain conditions, it allows flow of electricity. So semiconductors on its own are not allowing flow of electrons or the electricity. But we can make N junctions and P junctions using something called doping. So doping is introducing a foreign materials to the semiconductor material. For example, if you take silicon as the semiconductor material, and if you use or if you introduce boron into that material or the structure or the lattice, so the boron has lesser number of electrons than the silicon. So therefore, it creates a positive layer because there are some lack of electrons in that when you introduce boron into the silicon. So that can act like a p-type layer. And if we introduce a chemical like arsenic into the silicon, so arsenic brings extra electrons to the bonds or the structure or the lattice. So therefore, there you have now extra electrons. So therefore, we say that we have N-type layer. If you combine a P layer and N layer, we call it NP junction or the PN junction. So the P part is lacking electrons and N side is having excessive electrons. Though we have the excessive electrons and lacking electrons, still it is the potential is needed to let the flow of electrons. So therefore what we can do is we can stimulate or we can facilitate the flow of electrons by introducing a very tiny voltage. So if you connect the negative side with the negative or the N-type layer and the positive side with the P-type layer, now we are facilitating the flow of electrons and we say that the gate is open. And if you change the negative and positive sides, and if you connect the positive side with the N-type layer and the negative side with the P-type layer, now we are further increasing the resistance. So then we say that the gate is closed. To do this, we need only a tiny voltage only. And also we can make these PN junctions extremely small. So that is why the modern microprocessors have billions of transistors. Billions of transistors. And they need very little electricity. They generate very little heat. And they are extremely fast. And using these transistors, we can create, so transistor is an electronic gate. So by assembling these transistors, we can create logic gates. So what is a logic gate? A normal gate just facilitate flow of electricity or prevent flow of electricity. So it's just doing those things. But if we can make this facilitation or prevention based on logic, we call it logic gate. So in our day-to-day life, we use different logic operations. So we use the AND logic operator, the OR operator, the XOR operator, and the NOT operator. For example, someone might say you need both the passport and visa to enter into the country. So they are AND operator. Or someone will say you just need either passport or ID card to face the exam. That is O operator. So likewise, in day-to-day life, we use different logic operators. In business cases, day-to-day life, scientific and mathematical calculations, everywhere we use logic. So logic gate is an electronic gate that operates based on these logic. And these logic gates can be found in ICs or chips. Typically, a particular IC will consist of multiple logic gates. So let's quickly look at what are those Boolean logic gates are. The first one is the NOT logic gate. In the NOT logic gate, when you have the electricity as the input, the output will not be having the electricity. So we say that when the input is 1, the output is 0. And when you are not having the electricity as the input, you get the electricity as the output. Or else we say when in the input is 1, the output is 0. So it basically negates the value. So true become false and false become true. Or 1 becomes 0 and 0 become 1. So that is what is known as the NOT logic gate. So then we have the AND logic. So we all know that in day-to-day life, in AND logic, when both are true only, the result is true. Or when both are 1 only, the output is 1. All the other scenarios, output is 0. So then we have the OR logic. In OR logic, when at least one input is 1, the output is 1. When both are 0 only, it is 0. So it is something like when someone says you need to bring your ID card or your passport. If you bring ID card, you are good to go. If you take only the passport, yes, you can face the exam. If you bring both, still you can face the exam. Only issue is when you don't bring any of those. So that is where you are not allowed to face the exam. So these are not new things. These are the logic that we used in day-to-day life. So the third logic gate or the logic operation is exclusive OR logic operator. So this is somewhat hidden in day-to-day use, because when we say OR, sometimes we mean OR and some other times we mean XOR. In normal low operation, when both are 1 also we took it as 1. But when it comes to exclusive OR, the two inputs must be exclusively different. So therefore, this 1-1 combination is also considered as something result in 0 or false. So in day-to-day life, we use XOR logic. Only thing is we don't explicitly say. For example, when someone says, can you bring me tea or coffee? So that person is not expecting both. But we just use the word OR, but what we mean is XOR. But when it comes to computing, we can't say what I mean is this. So rather, we have separate logic gate called XOR. So now we are done with the basic logic gates, the NOT gate, OR gate, AND gate, and the XOR gate. So then we have 3 more compound logic gates. So those are not basic logic gates. Still, these compound logic gates are useful because there are plenty of places we can just build the concept using the NAND gate, NOR gate and XNOR gate. And there are some useful usages as well. So therefore we just take these three also as three different gates, though we can build them using the basic gates. So the first one is the NAND logic gate. The NAND logic gate is first we do the AND operation and then we negate it. So therefore the truth table is obvious. In AND logic, when both are 1 only 1, otherwise 0. Since we are now negating it, when both are 1 only 0 and all the other cases it is 1. So then we have the NOR logic gate. So that is the negation of the OR gate. Now when both are 0 only 1 and all the other cases the result is 0. That is an inversion of OR. And similarly we have the inversion of XOR gate and we call it XNOR. So earlier when they were exclusively different the output was 1. Now that is the case where the output is 0, and when they are the same now the output is 1. So that is called XNOR logic gate or the XNOR logic operator. So we can combine these logic gates to create logic components. Okay, so we call them logic circuit component. Just the simply use of AND, OR, XOR, yes, we can make some useful things, but when we combine these logic gates together, we can create some useful reusable components, and we call them the logic circuit components. So there are two types of logic circuit components in the computers. So we call them the combinational components and the sequential components. So let's briefly look at what are those two types of components. The combinational logic components are the logic components which does a well-defined task, and also the result does not depends on the current state or the memory. So that means whenever you give a particular input combination, always you are getting the same output. Whether it is in the morning or evening or whatever, for given input combination to a particular combination logic circuit, the output is always the same. For example, so there are some useful combinational logic circuit components like adders, decoders, encoders, multiplexers, etc. So we are not going into the details about these combinational or sequential logic circuit components because we will be discussing those in a subsequent session. So then we have the sequential logic circuit components. So the difference is in sequential logic circuit components, the output depends on the current state. So that means when you give the same input combination, depending on the current state, the output can be different. So that means they depends on the memory. And we use the sequential logic circuit components to build memory cells. So the memory cells are used in the registries and also in main memory. And these days we use the memory concept of memory cell to build our secondary storage devices like solid state drives as well. So we call them the latches of the flip-flops. So there are different type of flip-flops or the latches. The SR flip-flop, S bar flip-flop, JK flip-flop, D flip-flop. Right. So we will be looking at those things when we are doing the logic circuit components. And now we are in a position to understand the overview of the processor. So I told you that the processor is the device that does the processing of your data into information. So it's a complicated process and it's a gradual process. It involves so many steps. Here we just look at the big picture only. I told you that the computer consists of layers, the software layer, the firmware layer and the hardware layer. Ultimately, your processing has to be happen at the hardware level. But at high level, those things can be done at the software level as well. So when we say the things are done at software level, ultimately that those steps are handled at the hardware level. So when we write a program to process data using a high level programming language like Java, C++, so we have to compile that program and it will generate something closer to the machine code or the machine language. So machine language is ones and zeros with some meaning. But it won't be directly converted to machine language. It will be first converted to something called assembly language, which is in between the high level languages and the machine code. And that assembly code will be further converted to machine code or set of ones and zeros with some meaning. And that code will be executed. The program is set of instructions. So therefore, the processor is going to take those instructions one by one and do the processing. And of course, your program can have control structures like sequence, conditional processing, repetitive processing, and your processor is going to take care of all those things. And an instruction is taken to the processor and it is decoded so that it can understand the assembly code as the machine code. Now it is in a position to execute it, and now it is executed, and it continues for the next instruction, etc. And we call it fetch, decode, execute cycle. So therefore your processor has to frequently access the memory, because it is the memory where you have the program statements and also the data. So therefore your processor is frequently accessing the memory for the next instruction and also the relevant data. And then those instructions are decoded into the binary code, and then the decoded instruction is sent to the ALU for execution, and the ALU fetch the relevant data from the internal registries, and the result is written back to the registries and later into the memory. And from memory, time to time, your data will be saved to the secondary storage, because memory is volatile storage. So that is in very high level, that is how your programs are executed or your software is executed. But in between, we have to look at the role of the operating system, the role of the firmware, in order to properly understand this. So this is just a big overview only. And also I told you that your computer processor is heavily communicating with the memory and of course some other devices. So when it comes to communicating the data and instructions between different components, in the computer architecture we have a concept called buses. And these buses are something like lanes in the road system. So in some countries, in some places, we have the bicycle lane, the public transport lanes, etc. So likewise, in the computer bus, we have the sub buses, what is known as the control bus, address bus, and the data bus. So the control bus is used to send control signals between components, whereas address bus is used to send the addresses, especially the memory addresses. And data bus is the one that we use to transport data and instructions. We just call it data bus, but both data and instructions are transmitted using data bus. And if we extend the computer architecture a little bit bigger, now we have the central processing unit with the control unit, ALUs, and internal registries. And we have the bus architecture where all these components are connected together, they communicate with each other using the buses. And we have the memory, the secondary storage, and the input output devices and any other interfaces to network, etc. and they all connected to the bus architecture. So we have what is known as the system bus, and there are some sub buses as well. So this is little bit more practical view of the computer architecture and the computer motherboard. So this is our processor, and these are some buses connecting devices, and the CPU is connected to the memory, so we call it the system bus. And also, if we have a separate graphic processor, we need to connect that also, because the CPU and the graphic processor has to communicate heavily, and also the graphic processor has to communicate with the memory. So therefore these components are closer to the processor. Now if you look at the motherboard, you can see the processor slot, and memory is right next to the processor, and also these AGPs, so the accelerated graphic processor ports, are close to the processor, because they have to communicate and collaborate with the main processor. And usually we call that these devices are connected to the north bridge of the motherboard. So north bridge is a junction closer to the CPU. You can see in this diagram, the north bridge is somewhere here. So then we have south bridge, another junctions, and some other devices are connected to the south bridge or beyond the south bridge. So the devices like hard drivers or the SATA interfaces, some other connectors to the USB cards, the internet or the network interface cards, so they will be connected to the south bridge, and also the ROM. So that is just an overview. Of course, there are some concepts related to the different technologies. What is the difference between PCI and SATA? What is IDE? Right? So IDE is a little bit older interface. Right. So this is not the time to look at all those in detail. So this is just to give you the overview of the computer architecture. Right. So what we have not discussed in this particular session include the role of the firmware, and of course the role of the operating system. So those things we are going to look at separately on separate sessions. Right. If you recap what we have discussed so far, computer is a data processing device. It is used to do computing, and also computer is a general purpose device. The computer consists of combination of hardware, firmware, and software. Computer is a binary digital electronic device because it stores data and information in binary digit format, and also it processes the data into data or the information by applying Boolean logic operations. And the computer uses the component architecture as well. And also the computer uses the buses to communicate with each other. The programs are used to process your data, so it will be gradually translated into machine code, and the machine code will be executed by your arithmetic and logic unit. So that is just the surface of the computer architecture, but I hope you got the big picture. So in later topics, we will be looking at or dig into more details about this architecture as well. So if you feel like this session is useful to you, make sure that you like it and subscribe so that you will be getting more notifications on some of the useful topics that we will be covering. Thank you.